Hi everyone. I know that if you've had a chance to study the kernel of a linear transformation and the range of a linear transformation, if you've had a chance to do that, you might be wondering if there's a relationship between those two subspaces. Admittedly, the kernel of T is a subspace of V, while the range of T is a subspace of W. So in that sense, they're quite different from one another. However, if we recall this example here of a transformation from Rn to Rm by using a matrix transformation, so a matrix which would be M by N, right? If you think about it, the kernel of that transformation is the null space of the matrix. Right? We talked about that previously. And also, the range of the transformation is the column space of A. And there is definitely a relationship here. And the other thing to notice is that the dimension of the kernel of T in this example is just the nullity of the matrix, right? The dimension of the null space is just the nullity. Whereas the dimension of the range of this transformation is, of course, just the dimension of the column space, and we know that to be the rank of the matrix. And that should perhaps get some bells going off. There is definitely a relationship between the rank and the nullity, and I just want to remind you what that was. Anytime you take any matrix whatsoever, right, the rank of that matrix plus the nullity of that matrix always has to add up to n, which is the number of columns in the matrix. In other words, there is a definitive relationship between the dimension of the kernel of T, the dimension of the range of T, right here, right? The rank is the dimension of the range of T, and the nullity, which is the dimension of the kernel of T. Namely, they add up to n. N happens to be the dimension of Rn. It happens to be the dimension there. So somehow, it seems like there is a nice relationship between the kernel and the range here. Let's just explore that a little bit with another quick example. So imagine that we take T. We can certainly take a 2 by 2 matrix and spit out a real number. And we can do this via, all right, suppose I take A, B, C, and D, and I send this result to A plus D. All right? So this is a linear transformation. And I'm just going to remind you that if you set this equal to 0, what will happen is you're going to figure out the kernel. The kernel is a subspace of M2 of R. And what's going to happen is D is going to be free, C is going to be free, B is going to be free. All three of these variables are free, and A will be equal to negative T. So if you actually build a matrix according to these parameters, R, S, and T, this is what the matrices in the kernel look like. When you bust out those variables, as we've talked about many times, when you bust out those variables, you're going to be able to write down a basis for the kernel of T. So the basis here, I'm going to squeeze it in right here if that's all right. The basis is going to be, when I bust out the T, I get negative 1, 0, 0, and 1. When I bust out the R, I get 0, 1, 0, 0. And when I bust out the S, I get 0, 0, 1, 0. Okay. Now, what we can say is that the dimension of the kernel is 3. So on this example, I'm going to go ahead and erase here. The dimension of the kernel is 3. All right? So let's just write that here. The dimension of the kernel of T is 3. Okay, let's think about the range. How do we find the range? Well, remember, the range of T is simply the span of the transformation of a basis of M2 of R. Now, the easiest basis I can think of would just be the standard basis, 1, 0, 0, 0, right? And then 0, 1, 0, 0, 0, 0, 1, 0, and finally 0, 0, 0, 1. So the range of T would be the span of those 4 outputs of the transformation. Okay, so again, you can use any basis for M2 of R that you like, but this is probably the easiest one. Okay, well, if we transform 1, 0, 0, 0, remember all this transformation does is it just adds the diagonal numbers. If we add the diagonal numbers here, we get 1. If we do that here, we get 0. If we do that here, we get 0. And if we do that here, we get 1. Okay? Notice that we've spent $4,000 to get a spanning set for the range of T. And that's a big waste of money because, of course, we don't need to put 0 into the spanning set, and we don't need to duplicate 1 at all. So my basis here, my basis for the range of T is just simply going to be 1. And the dimension, if there's one thing in the basis, right, if there's exactly one thing in that basis, then the dimension is 1. So take a look. The kernel is 3-dimensional. The range is 1-dimensional. We were adding these numbers up in our first example up here. If we add them up here, we get 4. 3 plus 1 is 4. Where does 4 show up in this problem? Well, just as the n shows up as the dimension of the input vector space here in this example, the same thing happens here. M2 of R is 4-dimensional. So this gives us something that is worth writing down. It is generally called, well, the general rank nullity theorem. And we've now already seen 2 examples of it. I'm not going to bother to prove it today, but it is a fact that if T from V to W is linear, if we have a linear transformation, then there is a nice relationship between the dimension of the kernel of T and the dimension of the range of T. Namely, they are going to add up to n. They will add up to n for sure. Where n is the dimension of V. We usually use n for that, but I should just write it as dimension of V here. Just like that. Okay? So this is a nice relationship. Usually you're going to know the dimension of V on any given problem. And so you can play these 2 numbers off of each other. If you've done hard work to figure out the kernel already, and you know its dimension, well, then you're going to know the dimension of the range before you even start looking at the range, simply by using this equation. Okay, it's a really handy thing. Or maybe you know the dimension of the range, and you want to figure out the dimension of the kernel. Well, again, this formula would allow you to do that. Let's take a look at an example, another example where we can kind of take advantage of that. Let me get this out of the way as well. Let me just show you another example here. Suppose that we have T going from P3 of R over to P2 of R. Okay? And the formula is going to be that we take P of X, and we're going to output P double prime of X minus 3 times P prime of X. Okay? Now, again, to figure out the range of this transformation, I'm going to start with the range because in another video that I made, the range of T is something that we were looking at. So from the other video, the range of T is just the span of the transformation of this basis. here's the most natural basis for P3 of R is just 1x, x squared, and x cubed. And if you just transform those vectors, of course, when you transform 1, you get 0. When you transform x, you're going to get 0 here, minus 3 times the first derivative of x, which is 1. When you transform x squared, you're going to get 2 minus 3 times 2x, which is 6x. And when you transform x cubed, you're going to get 6x minus 3 times 3x squared, which is 9x squared. And the basis is just these three polynomials. So I have a basis. Okay, they are linearly independent and they span the space. We can throw away the 0 from that set. And so the dimension of the range of T here is equal to 3. So if you believe the theorem at the top of the board for this example, P3 of R is 4-dimensional, as we know. That's the input space. The dimension of the range is 3. And so we already know that the dimension of the kernel is 1 before we even calculate it, right? Before we even calculate the kernel, we know that the dimension would be 1. Now, how would you actually come up with that? Let's suppose we wanted to find the basis for the kernel. Well, that's not too hard to do. What you would need to do is take a polynomial. We would actually have to write out its coefficients, terms, and the different terms of this cubic polynomial like this. And we would just take the appropriate derivatives. So the first derivative, using the power rule, would equal that. And then the second derivative, if I just do it again, is going to be 6ax plus 2b. And then if I use that to actually write down the formula for the transformation, well, I'm going to have p double prime, which is 6ax plus 2b, minus 3 times p prime. So I would be subtracting 9ax squared, 6bx, and 3c. Okay? Now, remember, to figure out the kernel, you simply set this equal to the 0 vector. The 0 vector in P2 of R is just the polynomial 0. And you match up the powers of x on both sides of the equal sign. Of course, all of the coefficients are 0 on the right side. So for example, this is the only x squared term. And that tells you that a has to be 0. All right, so we know that a is 0. If we look at the x terms, I'm going to circle them. There's a term with x in it, and there's a term with x in it. 6a minus 6b would need to be 0. And let's see, is that right? That would tell me, yeah, that's correct. That would tell me that that a is equal to b, and that is therefore also equal to 0. Sorry, it's kind of late over here. So a and b are both 0, and then the constant term is 2b minus 3c, and if b is 0, then c is also 0. So a is 0, b is 0, c is 0, and we have only one free variable, which is d. And when you bust it out, you find out that your kernel of T is just it's just the set of all constants. That makes sense, right? When you take derivatives of a constant, that's how you're going to get 0 out of this transformation. Okay, because the derivative of constants is always 0. And my basis here, after I have busted out the T, my basis is just 1 itself. Okay, and so that's, of course, one-dimensional. So my kernel, as we expected, is exactly one-dimensional in that case. All right? Let's just look at another example really quickly. Suppose that we look at this transformation. I know I've looked at this one with you before. a transformation from R3 to M2 of R, right? And I'm going to take an input A, B, C, and I'm going to spit out a matrix. Let's just say 0, A minus B plus C, and minus A plus B minus C, and 0. Okay? We've already worked out in a previous video that a basis for the range of T was just simply the matrix 0, 1, -1, and 0. Okay? So the range is only one-dimensional. Right? The range is only one-dimensional. So if I put a 1 here, and I look at the dimension of R3, which is 3, I already know that the kernel should be two-dimensional. Let's check that. How do we do the kernel? We set the output equal to the 0 vector. And when you equate these matrices, you set the output equal to the 0 vector, you find out that A minus B plus C has to be 0. Sure enough, B and C are free variables, and A is simply B minus C. So your kernel of T, you could literally just write it as B minus C, comma, B, comma, C, such that B and C are real numbers. I'm just going to abbreviate it here. When you bust that out, when you bust out the variables on that, you can get a basis. So when I bust out the B, I get 1, 1, 0. And when I bust out the C, I get -1, 0, and 1. It's two-dimensional. Okay? So this is the general rank nullity theorem. And it's really nice to be able to take one of these dimensions and then immediately know what the other one is, just by looking at that equation. All right, that's pretty handy. I want to give you a couple of pieces of terminology here, just to add a little bit more to what we're saying. But I'm gonna save that, I think, for another short video. But this, hopefully, the general rank nullity theorem and the relationship between the kernel and the range, I hope it makes sense. And again, I'll be back with another video about one-to-one and onto linear transformations. Okay, I'll see you soon. Thanks.